Hello and welcome to our last session for our OptiBPM software. My name is Brian Tipper. I'm the VP of Sales and Marketing here at OptiWave, and I'll be assisting your host, Steve Dodds. The webinar today will focus on advanced applications of OptiBPM. As with previous sessions, we will launch 3 polls and we ask you all to please vote on these polls. We also have 2 question and answer periods at the halfway mark and at the end. And lastly, we'll be recording this webinar and emailing the link to everybody tomorrow at noon Eastern Standard Time, or sorry, at 2 p.m. Eastern Standard Time. With that said, let's get the webinar underway. I'd like to introduce your host, our OptiBPM Product Manager, Steve Dodds.
Hello and welcome to the OptiBPM seminar. OptiBPM is a software that calculates the propagation of light on optical waveguides. And today we're going to look at a specific application of that propagation. We're going to look at the propagation of light on optical waveguides that have been modified by an electric field, the so-called electro-optic effect. And to compare the results of OptiBPM with some standard, I have selected a paper from IEEE Photonics Technology Letters, and the authors of this paper did include enough detail to permit the reproduction, complete reproduction of their experiment by theoretical means, such as we could do by OptiBPM. On the right-hand side, I have reproduced their diagram of their waveguide. This is the transverse plane. It's a little bit of an upside-down kind of design. The cladding is BCB, a dielectric, and the substrate is air. So it's upside down from the usual configuration. And it includes 2 electrodes. And if a potential is applied across these 2 electrodes, we get an electric field that is seen by the waveguide in which the light is propagating. The materials as defined in OptiBPM also have with them electro-optic parameters. So the material gallium arsenide might have refractive index of 3.42, but we can also include some of their electro-optic properties. In this little formula, the capital E is the electric field that has been created by these electrodes. So it's an externally applied electric field, and that field could point in anywhere in the transverse plane. So it has an X component, meant EX, and a Y component, EY. The effect of the electric field, this is the linear electric optic effect, so the refractive index is changed by an externally applied field according to a coefficient, and the the coefficient for the horizontal component of the field might not be the same as the component for the vertical component of the field. In this case, it's only the horizontal component of the field that is influencing, sorry, only the vertical that is influencing the refractive index. The externally applied field could be a static field, or it could be radio frequency, but radio frequency from the point of view of optical field is a static field, since the radio frequency is much lower than the optical frequency. Another parameter that is needed for electro-optic calculations is the permittivity that is found at low frequency, static or radio frequency. The refractive index is for the optical field, but the permittivity at static could be something different. So including here is the permittivity for static fields or up to radio frequency. It's not necessarily the same as what we have at the optical. So this is how we enter the parameters, the relevant material parameters. And what I'm going to do next is just show how you would go about creating such structure in OptiBPM, applying electrodes, applying a potential, finding the electrostatic field, and calculating the resulting optical propagation. So I'm going to begin with snap to grid. That helps with the drawing of things. The horizontal axis is the direction of propagation. And I'm drawing a waveguide. I have already defined I've already defined the profile of these waveguides, so it's not necessary to redefine it here. And I have selected amongst various kinds of profiles the ridge waveguide. And what I'm doing right now is I am drawing just this ridge-like shape up here to show you. I can show you how the ridge was defined. It was defined to be a thickness 0.5 microns, and that's that thickness there. And I put slanted angles on the walls so that we'll get the walls that are inclined rather than vertical here. So having done that, I've drawn it. I can go to the 3D editor to have a look and see what this looks like. Oh, and there's now there's something not quite right. It is the vertical position of this ridge. In OptiBPM, the y is equal to 0 coordinate occurs at the top of the substrate, and for us, that's right here. So I'm going to need to change the vertical position of this. So 0 is at the air interface, so I've got 2, I've got 2.73, I've got 3.02, I've got 3.502, so I need to put that coordinate into the properties of this particular waveguide, and that is entered here in this depth field, and I need a distance of 3.05 away from the top of the waveguide. And the width is 4, and indeed the top side electrode is not, it's not 2. That's actually a mistake in my drawing. Sorry about that. It's 4. Trust me, it's 4. Okay, so we leave it there. And there it is. Let's have a closer look. And we can see that we've got some, at least the beginning of our shape is appearing. And we can look at this in an XY view as well. And we can look at it either in a window view, or I think for now I'm going to be setting this in a real dimensions view so we don't get too much distortion. So now it's kind of long and narrow, but at least you get the idea. So what's missing from my structure so far are some layers to go on top of the substrate. I need a 2 micron thick layer of aluminum gallium arsenide to go on top of the substrate. I need another layer of thickness 0.73 of gallium arsenide to go on top of that. And it's back to another thin layer of AlGas on top of that. There is a structure in OptiBPM. Let me save this so I can come back to it if need be. Today's Friday. Today's Friday, so I'll call this TGIF. Thank God it's Friday. Okay. So there is a structure that is convenient for creating layers that go all the way across. It's the so-called it's the so-called substrate region. And we can draw it anywhere we like. Its properties are all accessed from another dialog box. And I want it to start at the beginning of propagation and go right to the end of the wafer, which for us happens to be 12,000 microns, or 12 millimeters. And I selected, no, I don't want a second one, please. Just one will do. And I selected a propagation length of 12 millimeters because in the paper they did an experiment where they applied a voltage of 17.8 volts across the electrodes, and they observed how much propagation it would take for the optical phase to change by a factor of pi. And they got about 9 millimeters of propagation, so I made this a bit longer than 9 millimeters so that when I'm finished creating this whole structure and I apply the electrodes and everything like that, we should be able to observe it go through its full pi phase shift during the propagation. So I need to apply some layers to this, and this is done by adding layers one at a time. The first layer has thickness of 2 microns, and it consists of the AlGas material. The second layer has a thickness of 0.73, and it consists of gallium arsenide. And the third layer has a thickness of 0.32, and it is material AlGas. So if I've done that correctly, when I go back, yeah, it looks more or less right. So here are the layers that I've filled in. Let's see if we can get the scale out of this. That's at y is 0, and at the top y is 2. is the top of the all-gas layer, and 2.73 is the top of the gallium arsenide layer, and on top of that we've got our waveguide. So now we have reproduced the structure of that waveguide. The next thing that we have to put on this is these electrodes. And in OptiBPM, we achieve electrodes by drawing more waveguides, but waveguides of a different profile in order to identify them as electrodes, and that their function is to introduce static electric fields or externally applied fields. And I'll start with drawing the top electrode, and it is goes just parallel to the ridge. So I draw another waveguide, and I have a look at its properties. But I don't want another ridge waveguide. Instead, I select electrode 1. I set this up to consist of an electrode material, which I can later use for connection. And it has width of, yeah, that's right. It's the electrode that is a width 2, not the ridge. Right, so that is actually correct. 2 microns is the width of the electrode. So there it is, drawn on top of the ridge. And I think I probably forgot its y coordinate. That's right. Like the ridge, it's also at an elevation above the top of the substrate. So let's see if I got that right. Let's view this in 3D. It's easier to see in that view. And oh yeah, there it is. Little tiny electrode stuck on top of the ridge. And now I've got to draw the other electrode, the backside electrode, the ground electrode. So to do that, it's also parallel to the ridge. So I'm going to draw a third waveguide in the same position, but this one will have the ground electrode profile, and it's in a different Y position. It's at a Y position of, it's actually a little bit below the substrate, so it gets a minus 0.2 in order to get it to be in the right spot. So I say OK to that, and in order to make our view easier to see, I'm going to just arrange that layout view is sent to the back. Oh yeah, there was another thing I forgot. The width of that electrode is 6. It's not 4, it's 6. So there it is. You can see it behind the other 2 electrodes. And let's go back and have a look at our structure. Yeah, there it is. We've got an electrode on the bottom, an electrode on the top, ridge waveguide in between. And both the optical and electro-optic properties of all these materials are defined. So the next thing we have to do is connect the electrodes. I'm going to have to apply a potential to get any static electric field to appear in here. And so we have an editing tool of edit electrodes. So to the ground, I'm going to assign that an ID of 1, and the electrode I'm going to assign ID of 2. Ground I'm going to set to 0, and the electrode I'm going to set this to 17.8 volts because that's what they did in the paper, and I'm trying to reproduce the paper's results. So now I've got a waveguide structure, I've got 2 electrodes, I've connected them, applied a potential to the top structure. So that should be enough to do a simulation of the static electric field in the transverse plane. And we have an electro-optical solver to do this. And we press calculate, and it goes and solves something. And let's see what it found. Right now, it's only showing the electrodes. There's the the upper electrode and the bottom electrode. And now let's look at the potential. And it draws this as a bunch of field lines. And if I want to look in greater detail, I can move this up and down. That's the top electrode, which is at 17.8 volts, and then down to the ground electrode, which is at 0 volts. And we have a view of what's happening in the vertical as well. And I can also draw the boundaries of the refractive index, so you can see the ridge drawn in the same place as the electric field lines. Now that we've calculated the electric field, we can calculate some electrical properties that will be important for electrode design. The first one is a low frequency, like a bulk circuit element capacitance. So there will be a capacitance between these electrodes. It will depend on how long the electrodes are. And so it's just been calculated here that we're going to get about 1.2 picofarad for every millimeter that the electrodes are long. And that will apply as long as our electrodes aren't long enough to become a significant number of the radio frequency wavelengths. On the other hand, if you do drive these electrodes at high frequencies, then the 2 electrodes might start to operate like a strip line waveguide, and you'd get a transverse electromagnetic propagation going that way. If you drive at a high enough radio frequency to make these electrodes traveling wave electrodes, expect a wave impedance of about 79 ohms. And you can expect that the phase velocity of the traveling radio frequency wave is going to be about 1/3 of the speed of light. Okay, I like to break here for give us a chance to read a couple of your questions so that we can answer them. And Brian would also like to ask you a few questions in the form of a poll. So see you all again in a few minutes.
Okay, thanks, Steve. Second poll is up for everybody. Please go ahead and take a chance to answer that. And also, we do have a couple questions in, but we'll take as many questions as you guys have. So please go ahead and type them out now if you have anything generally BPM related, Steve's the guy to ask. He's the prog manager expert. He's the all-knowing BPM guy that we have. So please take the opportunity to type your question out and figure out whatever BPM application that you're working on or scenario if it's capable with our tool. So with that, I'm going to go ahead and close the poll down, and hopefully Steve's had a chance to read through some of those questions.
Thank you, Brian. Yes, I do have a couple of questions. My first is from Ahmed, who asks how to model a double clad fiber. And well, that's not too hard to do, but you'll just have to use different sorts of profiles. Here, in my project that I've made today, I've been using profiles that are channel type profiles. But if you make profiles that are fiber type profiles, it'll ask you to put in a bunch of layers. Now here where the layers are radii, semi-radii, Rx and Ry. And if you set down here, like select one of these, if I selected that to be a fiber profile instead of one of the channel profiles, then you would see a circular shaped thing in the transverse plane. And yeah, you can put a number of claddings on those. You can even create them in the shape of electrodes. I actually did that for my QA testing because there aren't too many shapes where you can calculate yourself what is the capacitance and wave impedance in concentric circles like coaxial cable or something like that is one of the only ones I know. So I have actually done that. So anyway, it's not a big deal modeling double clad, triple clad, how many other clad fibers. Okay, I have another question about what we see in this picture. We see in this picture, or I guess it's a little bit more clear in the height plot view. These turquoise shapes are actually the electrodes, and they appear in the plot of refractive index in the refractive index in the xy plane, the refractive index in the transverse plane. They do appear because the electrode materials, both the ground and the electrode, they do have refractive indices defined, and that's why they actually do appear in the refractive index plot. These refractive indices are not really used in the simulation because electrodes are usually defined such that they aren't close to the optical field. So theoretically, I could set this to be anything, and it wouldn't affect the simulations that are going to follow. But I did set them to something such that they would be at least visible in our plot, because it is nice to be able to see where the electrodes are. Okay, I have another question. Do you have the capability to orient the material optical axis in any direction? That is, in the case of uniaxial materials, not gallium arsenide? Well, yes, we do have the capacity to change the orientation. I'll show you what we've got. And in any of these materials, like gallium arsenide, for example, I'm using an isotropic refractive index, and I'm using an isotropic simulator. But I don't have to do that. It could be an anisotropic material if I wanted to do that. And in that case, I would be able to put non-zero numbers in the off-diagonal elements of the permittivity tensor, indicating that even if I do have principal axes, they're not coincident with X and Y. So yeah, we can do things where the optical axis is something else, but not anything. I believe that you do have to have at least the principal axis coincident with the direction of propagation. It's my opinion. I've tried for a number of years to prove this. I haven't succeeded yet, but I do believe that if the axis of propagation, that is, if the horizontal axis is not coincident with the principal axis of the crystal, you don't get modal propagation. It just doesn't exist. You get birefringent propagation, which is a different kettle of fish. No, we don't do that, but that's generally not used in waveguide analysis because the propagation isn't modal. Waveguides are for modal propagation. Yeah, so that's what I have to say about that. All right, I have calculated I have reproduced this structure. I've calculated what the electric field looks like if one applies a specific voltage across the electrodes. Now I would like to do a simulation of optical propagation along this waveguide. To do that, I have to arrange an excitation. I have to put some light in the left end of the layout because my propagation is going from left to right. So to that end, I'm going to put down what we call an input plane, and this is where we specify what the excitation will be. And I would like my excitation to start at the beginning of the wafer, in which at this point the z coordinate is 0. I want to use a modal excitation, and to do that I'm going to have to find out what the mode of this optical waveguide is. And when I go to the input field dialog box, I get a list of the waveguides that cross the input plane. There are 3 of them. 2 of them don't interest me because 2 of them are electrodes, and I'm not forming my waveguide, optical waveguide off the electrodes. I'm forming it off the ridge waveguide. So it's only the ridge waveguide that I wish to participate in the calculation of the optical mode. So I select the one I want. There it is. And then I call the mode solver. I'm going to do a semi-vector calculation, a semi-vector of light polarized in transverse electric, because that's the excitation I'd like to use. And that's what was used in the paper as well. And I go calculate my mode. It shows me first the refractive index distribution. and then it shows me the mode that it found on it. So as you can see, it does indeed exist mostly in the high index gallium arsenide layer. There's a little bit that extends into the ridge and a little bit below the gallium arsenide slab, but not a lot. It's mostly just existing inside the gallium arsenide film. And the electrodes are above and below that, and they are going to influence the optical field by changing the refractive index slightly. Okay, and I'm going to ask for a little bit of additional output data for this. There's a whole bunch of things you can ask. It's always good to see relative power versus distance. And since this is an electro-optic calculation, I'm going to ask to see the electrode impedance. That we won't see too much with our design because we haven't changed the electrodes in the course of the propagation. But if we did make the electrode wider or change it somehow during the propagation, then the impedance would change. It would be useful to observe that. It's good to put in a few Z cuts. Let's see, maybe something interesting happens at a distance of 5,000. I don't know. Maybe we'd like to see the refractive index there too. So just making a shopping list of things that we might like to see after the simulation is finished. Okay. So we've specified what the electric field is at the beginning of propagation. I'm now going to run the BPM simulator, which will calculate step by step, one step at a time, what happens as we proceed down the wafer. So let's run. And it begins by finding the mode. I'm going to view this in the propagation direction. So what we're observing right now is the electric field amplitude, and nothing's changing here. It's a good waveguide. But let's observe the phase. Something is happening on the phase. It did start with 0, but as it progresses, the phase seems to be changing. And I'm interested at the point that it's gone through pi shift, and yes, I get a shift of pi at about 9 millimeters of propagation. And that does happen to agree nicely with what was observed, or what was reported in the paper that I quoted. Let's look at the phase again. There it is. Let's just make a graph of it, and like that. And let's look at what's happening in the middle, where the waveguide is. And yes, we start with a phase of 0, but as the propagation proceeds, it shifts, and after about 9 millimeters of propagation, it goes through a shift of pi. And that was what was expected with this voltage, this applied voltage. So there you have it, electro-optic simulation of waveguides by the beam propagation method. Hope you enjoyed this little presentation, and maybe we'll see you all again sometime in our next webinar sequence. Goodbye and have a good weekend.
Thanks, Steve. So just the last poll before you guys go ahead and take off would be appreciated. We don't have any questions at this time, so as soon as the poll completes, we're just going to go ahead and end the webinar. We have one more session scheduled on FDTD in an hour and 20 minutes from now. So if you are interested in that, please go ahead and sign up if you're not already. Otherwise, thank you everybody for attending, and I hope you enjoyed all these sessions to this point. Thanks.